Hey guys, so this next section that we're going to be dealing with is conformation of alkanes. We're going to be looking at carbon chains first, so we'll deal with ethane, we'll look at butane, and then we're going to start looking at some chair conformations. It's really exciting stuff. Might be the first time that you start getting your model kit out and playing around with it. Alright guys, so let's take a look and examine what the conformations are of ethane. So ethane is a fairly simple molecule to look at. So of course it's a CH3CH3. Now if we look down this carbon-carbon bond, the H's that are pointing up like this are actually going to be along the same plane essentially as we look down this. So they're going to be right on top of each other. And same with the H that's out here, those are going to be eclipsed, and the H's that are back will be eclipsed with each other also. However, if we take one end of the molecule and we rotate it around, like this end specifically, if we do a rotation like that, that H that's up here on the top would move essentially down to this position. And then if we look down that bond again, this direction, this H would fall perfectly between these two H's. And we call that staggered. So we can see that a little bit more clearly looking at the following video. So you can see the ethane molecule here. We have free rotation around this carbon-carbon single bond, right? So if we look at this head on, you could see that rotation occurring. Now, as the H's come close to each other, there's a repulsion because the electrons in those bonds repel each other. So there's a high energy and a low energy conformation that we see there. So this is a view, a static view of the low energy conformation. So we see a staggered conformation here between the H atoms, right? So there's an H atom coming out at us and one going back here. So this is kind of like this side view, right? We pull it around and it looks like this. That's how we would often draw that. And then we also have this eclipsed view. So this view is along the carbon-carbon bond, right? Here's your side view. So if we rotate it around, we can see those H's perfectly on top of each other. That's a high energy conformation. So those two conformations that we have, that we saw eclipsed and staggered, they can be drawn out in something called a Newman projection. So these Newman projections here are going to have kind of two ways that we're going to be looking at them. So what we're going to do is we're just going to put a bullet right here in the front for right now. That bullet's going to represent a carbon. Now off of that carbon, as we look down, like specifically, like why don't we take a look at this one? As we look down that carbon-carbon bond here, what you're going to see is that that atom that's in the front right here has three bonds to it, three H's, right? So there's going to be an H that's pointing up, right? Then there's going to be an H that's going over to the left and over to the right here. Right, now in the back of this, there's another carbon right here. So I'll just use a red for that. So it's hard just to draw a dot there. So instead we just draw this circle to represent the back carbon. So they're totally on top of each other. Right, and in this case, we still have an H that's pointing up right here, but we can't draw it perfectly there. So we just kind of move it over to the side just a little bit like this. Right, now so we come over here, these H's here are going to be eclipsed with each other too. So we're going to put an H like that. And then the H's that are pointing back right here are going to be right over here, and we're going to show them just like this. Okay. Now the angle that we have between these two, as we look down that carbon-carbon bond, as we did that before, if you go back and look at that animation, we call that the dihedral angle. And that dihedral angle is 0 degrees because they lie perfectly on top of each other there. All right, so that'll be a high energy. Now if we look over at this other side here, right, let's use blue. So this little dot right here is the carbon that's in front. We'll put that right there. So that has an H that's pointing down here, and then one that's going over to the side and the other side, the left and the right hand side. And then that back carbon here is going to be that back circle there. And sticking off of this, as we look down here, that atom right here is going to be pointing up, right? And then we have an atom that's going to be on the right, and then an atom that's going to be on our left, like this. Right. Now, this is called the staggered conformation. And this angle, again, is the dihedral angle, and that is going to be 60 degrees. So there's a different energy associated with each of these because having these H atoms eclipsed on top of each other costs energy, right? Just think of VS EPR. The electrons that are in those bonds want to repel each other. So if we look down below here, we can kind of plot these things out. Remember, eclipsed, higher in energy than our staggered. So let's go ahead and let's put in our atoms here. So, right, these are all H's right now. So here we have eclipsed. So that eclipse energy, high. I just put a point somewhere up here. Okay, and next after that, so here's our eclipsed. Next we have staggered. And we see a rotation there that takes that H and moves it over here. So what we're doing here is we're keeping the back carbon stationary and removing the front. So that H that I just circled moves over to this position. Right? This H that's right here moved to this down position, and then this H that's right here moved over to that position. Now that will have a lower energy, so we're just going to put a dot down here at the bottom. And we're just going to cycle through this, right? So again, putting all of our H's in, just like so. This H that's here moves over to this position. So again, it's in the front right there. Right, this H that's here comes over to here, so that's right there. Right, and this H that's there moves over to this position, and it's now right here. That gives us another eclipsed conformation, and that gives us the same energy as we saw before, right? And you can see, so again, another 60 degree rotation. Let's put our H's in, keep track of where they are specifically. So here, they're all H's, so it doesn't technically matter, but it's going to soon. So we're going to move that here. That's this H. This H is going to come over to this position, so that's right there. And then lastly, this guy comes over to this position, which is right here. And again, that's a low energy now. Now we connect all these, trying to make a nice curved line, and we get something that looks like this. And we'll just do here, etc. So on and on and on here. Now this leads to something that we need to talk about called torsional strain. That is the strain that's caused by the resistance to twisting. So again, it's the electrons that repel each other in those nearby bonds. It's also sometimes kind of like our delta G. And again, the other thing to notice here is that your staggered conformation is always the lowest in energy. So you can look up this number, but this energy difference right here is 12.6 kilojoules per mole. So that's your energy barrier to rotation of your ethane there.